Thank you for taking the time to watch our ProSeries monthly webinar by Protect. The ProSeries content is designed to bring new ideas, strategies, and understanding of topics that help ensure people and processes are safe, equipment is reliable, and companies remain compliant with applicable regulatory jurisdictions. To ask a question, please click the Q&A icon at the bottom of the screen to type your questions. We will answer them as they come in or hold them to the end of the call. My name is Nathan Vandergreen, CEO of Protect, and I will be your host today. We have a great topic to share with you with regards to what we believe is a meaningful topic regarding layers of protection analysis or LOPA principles for an effective hazard and operability analysis or HAZOP study. With that, and without further ado, I'd like to introduce you today to Greg Hill, Senior Process Safety Engineer at Protect. And Greg, could you take a few moments to give a brief snapshot of your background?
Morning, Nathan. Thank you all for joining today. As Nathan mentioned, my name is Greg Hill, and I have a master's degree in chemical engineering from Newcastle upon Tyne University in the UK. I started my career as a functional safety engineer, providing consultancy services to mostly major oil and gas producers throughout the Middle East, Europe, and the UK. I spent a lot of time facilitating and scribing PHAs, HAZOPs, hazards, LOPA workshops, conducting what they call safety integrity level, SIL verification and safety requirement specification development for safety instrumented functions, performing consequence modeling and QRAs, and general functional safety consultancy services in accordance with IEC 61508, 61511 for the process industry. I then took a role with WSB on the process safety team, where my efforts were mainly focused on providing functional safety and process safety services for a major UK LNG regasification project. And a little over a year later, I made the move to sunny Southern California, where I've joined Protect in June this year, and I have been actively involved in facilitating PHAs, HAZOPs, some LOPAs for the energy industry, and general development of LOPA services and functional safety activities too.
Great. Thanks, Greg. Appreciate it. And today we're going to be discussing the application of LOPA principles for an effective HAZOP. But before we dive in, Greg, could you provide a brief explanation of HAZOP and LOPA and really how they differ?
Absolutely, Nathan. So HAZOP, or HAZOP study or analysis, as it's often called, is one of several process hazard analysis methods, PHA methods recognized by OSHA's Process Safety Management Standard for risk identification and evaluation. So it is a systematic method used to review existing or new facility designs to identify and address potential hazards or possibly operability problems that may or may not be present in industrial processes and designs. So it involves what we call a qualitative evaluation to assess the potential risks towards people, assets, company reputation and environment, and others depending on any of the company requirements too. So LOPA, on the other hand, this is a risk assessment tool that evaluates the adequacy of existing or proposed safeguards that serve to protect or mitigate hazardous scenarios in process industries. So this is what we employ, what we call a semi-quantitative approach. So combining both qualitative and quantitative methods to estimate the frequency and consequences of undesired events, and then compares them against a predefined company risk criteria, which is quantified. So a key distinction between the two, between HAZOP and LOPA, is the utilization of safeguards and independent protection layers, or IPLs. So there's actually a well-known saying in the LOPA world, and that's all IPLs are safeguards, but not all safeguards are considered IPLs.
Great, Greg. Thank you for giving that insight. So what are some of the key differences between safeguards and IPLs? And perhaps you could share a few examples.
So safeguards are typically identified during PHAs or HAZOP studies, and they have the common aim of reducing the overall risk. So these are considered devices, systems, processes, or human actions that aim to disrupt the chain of initiating events either by preventing the likelihood of consequence or by mitigating their severity. IPLs, on the other hand, these are utilized in LOPA, and their effectiveness is quantified in terms of its probability of failure on demand, or PFD as we like to abbreviate. So again, we consider these to be devices, systems, processes, or human actions capable of preventing a scenario from proceeding to the undesired consequence without being adversely affected by either the initiating event or by the actions of any other protection layer associated with this scenario. So generally in HAZOP, we look to identify all relevant safeguards, and they could be strong or weak. Whilst in LOPA, we validate these safeguards as potential independent protection layers. So examples can range from BPCS, control alarms and trips interlocks, to containment berms, or we call that bunding within the UK, and fire and gas detection systems.
Okay, that's interesting. So how do we go about validating safeguards as IPLs?
First of all, the Center of Chemical Process Safety, or CCPS, has defined what they call 7 core attributes for a safeguard to be classified as an IPL. So they are independent. So this needs to be independent from the initiating event and other protection layers. Functionality, so it needs to be able to operate to completely prevent or mitigate the consequence. So for example, being able to respond within the required or stated process safety time, or this could be a relief valve, being able to handle the full overpressurization case. Your integrity, so being able to reduce the risk by a specified amount as reflective of the design and management of the protection layer. So this reflects what we claimed earlier to be the probability of failure on demand, which is a quantitative value. Needs to be reliable, so being able to operate as intended for a specific duration under all relevant conditions. Auditability, so having established design, installation, functional testing, and maintenance regimes in place, which effectively verify the effectiveness of the IPLs. Access security, so measures to protect against unintended and intended physical or cyber attacks. And management of change, so this is having a formal process in place to review, document, and authorize modifications on any safeguards and other process elements before their implementation. So given that each company is typically different, and each have their own specific guidance on what they may qualify or may not qualify as IPLs, but generally there are 3 fundamental core attributes that are most widely and commonly used. So these are independence, functionality, and auditability.
Okay. It sounds like a lot of requirements to fulfill. Can you elaborate on those 3 core attributes and explain why it's considered important?
Yes, so independence is a big one and arguably one of the most important in my eyes. But independence is ensuring that the effects of the initiating event or other IPLs or independent protection layers do not interfere with a specific IPL and thereby degrade its ability to perform its functions. So for it to be effective, it needs to be independent from the occurrence or consequences of the initiating event and from failure of any component of an IPL already credited for the same scenario. So a common example here would be a control system failure, where you've got your level transmitter going to your logic solver to your final element. Any failure within that loop, which would typically render everything within that same loop to fail also too. So industry guidance does allow for sharing of BPCS layers, but certain rules do apply. So first, they must be 2 functionally separate independent controllers, safely sharing information using a common communications network, and must be properly designed and managed. Secondly, the communications network must provide a high degree of protection against system data corruption and be segmented to provide protection against unauthorized access. So failing to demonstrate any of the above would mean they cannot be claimed as valid IPLs. So let me show you 2 examples of independence. This first one is what I call the ideal approach, where you can see the sensors, input-output cards, the CPU, and final elements are all separate and completely independent from one another. The second example is what I call the acceptable approach, which is based on the above principles. So here, again, we have the separate sensing, input-output cards, and final elements, but as you can see, we have sharing of the CPU. Now, as long as the rules above apply with respect to being able to safely share information between two controllers and being properly segmented, we can claim independence for this example. But in any case, I always advise that air gap independence is recommended. Another two important attributes to consider whilst validating safeguards as IPLs, and I've actually combined them here since I think there can be a lot of crossover between the two, and that's auditability and functionality. So is there a testing, maintenance, training regime in place for the respective IPLs? Because I know all too often I see and hear about protection systems, whether they're mechanical, programmable, electronic being installed, and they're actually left with no periodic testing or maintenance being done on these equipment. And these could be left for years at a time, and it's very likely that these will not operate as originally intended. You know, it's important to note that equipment do undergo wear out, and it's extremely important to audit and validate these periodically to ensure that their effectiveness is maintained and they're designed to do what they're intended to do. Another point when identifying these safeguards or IPLs in HAZOP is asking the question about whether these are functionally apt for the scenario. So I did mention this earlier, but is there enough time for the operator to respond in the event of alarm? So, you know, are we talking a matter of seconds, or do we have minutes or hours for the operator to take corrective action? Can the trip or interlock respond within the process safety time? Has the pressure relief valve been sized for the identified overpressure case? And is there adequate documentation to prove this? So conducting these checks reinforces design confidence and ensures a healthy and safe operating plan. Again, if failure to do any of above means they cannot be claimed as valid IPLs.
I think from the explanation there, Greg, can definitely see the importance of validating these to ensure system reliability. So how do you propose incorporating these principles into a HAZOP study, and why not wait until LOPA to do so?
So LOPA demands extensive expertise and specialized skills. It can be quite a tricky one to navigate. And I know many facilities don't often conduct additional studies beyond HAZOP. So for those reasons, that's why I incorporate basic LOPA principles into my HAZOP studies. And this is to ensure that all hazardous scenarios are well protected and for general effective risk management as well, even if the risks are deemed or may appear acceptable. So even applying at least 3 of the common attributes outlined by the CCPS will ensure that you're well on your way for having a robust, safe system in place. Now, there is actually one useful approach I often employ, and this is part of the CCPS guidance. And this is the key reminder for IPL's guide. So to start, assess whether the safeguard qualifies as a candidate for an IPL or an independent protection layer. And we can do this by applying the 3 Ds. So detect, decide, or deflect. So detect, most IPLs detect or sense a condition in the scenario. Decide, many IPLs make a decision to take corrective action. Or deflect, all IPLs deflect the undesired event by preventing it. Next, we can assess the effectiveness of the proposed IPL by addressing the 4 enough questions. So is it big enough? So this could be a containment berm. Is it fast enough? So can it operate within the process safety time? Is it strong enough, or is it smart enough? The big I serves as a strong reminder to verify independence, ensuring that the proposed IPL is independent from the corresponding initiating event and other IPLs. And finally, probably one of the most important as well, is ensuring that there's a robust testing and maintenance regime in place, supported by adequate documentation for proof of functionality, as confidence in the design is key.
Great. Would you walk with us through a worked example on how you would implement the above LOPA principles into the HAZOP study?
Absolutely. So here we have a knockout vessel and we have a two-phase feed coming in. There is liquid drawer from the bottom of the vessel, which is controlled by the level control. So that's LIC 001 via pump 001. We also have gas exiting the top of the vessel, which is routed to downstream units. This could be a compressor, for example. So as you can see, we have a independent level trip, which is LT002, and that has a LAHH and a LALL configured to the level transmitter. So the LAHH002, that acts on the upstream valve, which is ZV001 in the event of high level. And the LALL002, that acts on the downstream valve, which is ZV002 in the event of low liquid liquid level in the vessel. So this particular HAZOP, and we're going to sort of run through this hypothetical case. We have causes for high level here. So the HAZOP has identified following causes for high level in the vessel. So we have pump 001 failure. We've also got a ZV002 failure, closure failure, and we've also got more flow received from upstream. So our task here is to review and validate whether LAHH002 safeguard is a credible IPL for all causes identified. Okay. So what I've done here is I have tabulated the different types of causes that have been identified in the HAZOP into this table. You may or may not agree with the approach I've done, but just for the sake of this workshop, I think it's just keep it fairly simple. So our first causes are all related to the pump failure. So we'll start with independence. So as you can see, pump 001 fails. This could be due to a mechanical failure. So since we're dealing with a pump failure and it's mechanical, and aside from the fact that it's completely independent from the level transmitter, we can claim independence in this case. Secondly, we have pump 1 incorrectly stopped due to failure in LIC 001. So this is an actual control failure within that control loop. Since we're completely independent from the level transmitter, we can claim independence and are given this a green tick also. Now we move on to the ZV. So you can see the ZV002 failure due to loss of instrument air. So instrument air is supplying this valve. If we lose instrument air, then we will drive the valve closed because it's a failed closed valve. Now, because it's an instrument air and not control failure, even though part of the same control loop, we can claim independence here. And I've given this a green tick. We've also got a cause for ZV002 closed due to human error. So this could be to avoid any downstream upsets. Again, since this is a human inflicted error and has not rendered the control loop as failed, I've claimed this as being independent also. So given this a green tick. Now, we have a ZV002 incorrectly stopped due to failure in LT002. So our control loop failure with the level transmitter reading low. So this is a credible cause. You hear about this in industry quite a lot. Level transmitter is reading low, which is as a result has shut the following ZV closed. Now, since we have a failure in our control loop, or in this case, our level transmitter, which is doing the reading, is faulty, we cannot claim independence from that LAHH002 because we're relying on that same level transmitter to implement that action. So as a result, I have given this a red cross and it is not independent of the IPL in this case. And then our last one, we've got the upstream unit sends flow rate in excess of the maximum normal flow rate. So assuming that we're completely independent here, which we are, I've also given this a green tick. Now, on to auditable. So since we're in a hypothetical HAZOP case here, and for the basis of this example, I've discussed with the company and they've proven to me they've got a testing and maintenance regime in place for the LAHH002, and they've shown me the documentation. So therefore, I have given all these cases a green tick, and this validates the auditable criteria. Now, moving on to functionality. So for LAHH002 to be considered a valid independent protection layer, it must operate as intended. So during the workshop, it came to our attention that the feed rate supplying the vessel is exceptionally high. So there is a case where we could potentially fill the vessel within a matter of seconds. So this indicates an extremely rapid process safety time. So having discussed this with the company, they were unable to confirm whether the calculation and verification of the interlock's ability to respond within this time had been carried out. So because of that, I have then therefore raised an action to review and ensure that the interlock can indeed act within the process safety time to bring the process to a safe state. So in response to this concern, the action has been raised, and due to that, I cannot validate this as a valid IPL. So I've given this a red cross. So just to summarize, we had an IPL that exhibited independence from 5 of the 6 potential causes, providing a substantial level of protection. We had verified periodic audits, testing, and maintenance in accordance with the device specifications, thereby satisfying the auditable IPL criteria. Now, because of the functionality of this IPL could not be confirmed due to the extremely short process safety time and the lack of evidence demonstrating its ability to operate within that time, I have concluded that this safeguard cannot meet the criteria for being a valid IPL. But it's worth noting that if the response time can be verified to be less than the process safety time, then this safeguard could potentially qualify as an IPL in the future. So it's worth noting for that.
Very detailed, Greg, and great example. Thank you for that. Could you summarize what we've discussed today?
Absolutely. So summarize, safeguards are identified in HAZOP studies, whilst LOPA validates these safeguards as potential independent protection layers. So as such, all IPLs are considered safeguards, but not all safeguards are considered IPLs. We know that CCPS has proposed 7 core attributes for validating safeguards as IPLs, with 3 considered to be the most used, and those are independence, auditability, and functionality. By evaluating the safeguards as IPLs at the HAZOP stage, what we're effectively doing is expediting any subsequent LOPA studies. So all we're really doing is helping in the LOPA judgment process, which could save valuable resource time as well. This is particularly beneficial for larger studies too. Finally, by integrating LOPA principles into HAZOP studies, we can instill confidence in both the design and management of IPLs, whilst also ensuring we have a well-protected and safe process.
Again, thanks, Greg. Appreciate that. Before we take questions, I wanted to bounce back to the independence, or excuse me, not the independence, but the just the list of the various parts and pieces that when you look at validating the safeguards of IPLs, and it's no surprise to anybody on the call, but we perform a lot of different risk and compliance and reliability services for hundreds of different customers across the nation. And when you look at this list of everything from independence to functionality to management of change, it's really what drives significant incidents within industry. So just to put a specific plug in there for this is understanding if these things are sized right, if they're functional, if they make sense for the process is just absolutely paramount in terms of seeing the types of incidents we've seen as a company through the years of doing this. So just wanted to make sure that that point wasn't missed there. I know many people are waiting to understand more about LOPA principles into the HAZOP world. We're going to take a moment to answer any questions that have been submitted to by our listeners here today. So first one I have here, Greg, that comes up is there a limit on how many IPLs we can credit for a given scenario?
No, but there are restrictions on the extent to which we can rely on a BPCS protection layer for a specific scenario. So according to industry guidance, and I say industry guidance, this is the IEC 61511, 61508, and it's the ISA 84 here, which is considered as RAGAGEP, I think, for in accordance with OSHA. But they basically provided guidance of a maximum of 2 BPCS credits per scenario. So this could involve 1 BPCS credit as part of the initiating event and another as an IPL. Alternatively, in cases with non-BPCS initiating events, such as a human error scenario, a maximum of 2 BPCS IPL credits are permitted. And this limitation is in place to prevent an excessive dependence on BPCS IPLs, which can pose challenges in demonstrating the independence between them. And just to sort of elaborate further, the BPCS could be alarms, it could be a control action, even an interlock, which is considered as part of the same loop as well. So regretfully, it's limited to a maximum of 2 cases, but for good intentions though.
Appreciate it, Greg. Another one we have here is, what is the process safety time and response time? How would I go about determining that?
Okay, the process safety time is the time period between a failure occurring in the process or the control system and the occurrence of a hazardous event if the interlock or the safety instrumenting function was not to perform. So effectively, it is the amount of time available to take corrective action to bring the process to a safe state after detecting an out of control condition. On the other hand, the response time, this is the time it takes for the interlock or SIF to sense, make a decision, and initiate the actions required to bring the process back to a safe state. So this includes the time for the sensors to detect parameter changes, the logic solver to process information and send a signal to the interlock or SIF's final element, and the time required by the final element to act. So for it to close a valve. Quite often, the valve closure is usually the longest part, and we usually go by 1 inch per second. So if you have a valve which is 10 inches, then generally it takes about 10 seconds for it to close. So typically industry guidance recommends that the response time of an interlock or SIF should be less than or equal to half of the process safety time. And this buffer has sort of been provided to account for any uncertainties there may be in the system modeling, process dynamics, measurement inaccuracies, measurement delays, and potential for performance degradation over time, really. So all of these can be quite difficult or impossible to precisely calculate. So just having that buffer there will ensure that your interlock can respond within that dedicated, that calculated process safety time.
Another one that came in here, Greg, is, this is probably a loaded question, and I realize it's going to be different based on the facility we're talking about, but how long does the LOPA analysis take, or the study take? Who do you involve? And again, knowing it's probably a loaded question in terms of time based on a per unit, big or small facility, so on and so forth. So let's see how you can answer that one.
Yeah, it's a good question. It depends. So big facilities, there's 2 ways of doing it. Generally, and if you're following the life cycle approach, which is IEC 61511, you would perform your HAZOP studies, and then any major hazardous scenarios that you identify, if you're potentially killing a lot of people, or if it's very difficult to see if you're well protected, then they are generally fed forward to the LOPA, which is the next stage. But what I'm seeing a lot these days is integrating a LOPA and HAZOP workshop as one. So kind of like what I spoke about today about implementing LOPA principles, but going through each causes and ranking them based on whether they're IPLs, and providing a PFD, or what we call a risk reduction factor, which is effectively the inverse, and doing it like a mini LOPA as you go through. Any cases where it's quite difficult to, and that needs sort of more thorough analysis, then we can export that to a sort of a detailed LOPA worksheet where we can look at taking credit for occupancy and probability ignition, and sort of look at the scenario in granular detail. So it's a bit of an open question on how long it can take, but I think the days of doing it in 2 separate studies, we can integrate it as one. So we're able to do a HAZOP and LOPA side by side. So, generally for the amount of time it might take to do a 5-day HAZOP study, we might implement an additional day or 2 just to to make sure that we integrate it with a LOPA approach as well.
Perfect. Looks like I have one more here, and based on the incidents that you've kind of seen across industry recently, it seems like there's been a fairly significant amount of explosions, fires, just bigger process safety related incidents in the last couple of years across all, I would say across all energy, petrochem industries. Where would you rank this type of study and priority for those industries to really put on their priority list?
I'd say it's critical. And a lot of the incidents we're seeing, they could be human error related, and that's not following procedures properly. It could be down to auditing, management of change. It's important to do the LOPA. And I think if we were to apply these LOPA principles and validating these safeguards as IPLs, rather than just saying operating procedures, it's making sure that it's in place, that it's being audited every year, ensuring that your operators are trained, well trained. One of the requirements is ensuring that your operators fully understand the interlocks requirement for being there. So in the event of something happens, they know what it needs to do, what hazardous scenarios it's protecting against. You've got to make sure that you test these yearly to reveal any hidden dangers, any hidden failures. So yeah, LOPA is really, really important. I think it's a very good risk assessment tool, one for identifying and actually seeing, do we have a scenario here that's well protected? And quite often you've got all these control systems that are in place, but in reality, based on the guidance provided for LOPA principles, you're only limited to BPCS protection layers that you can take credit for. So that leaves quite a significant gap that you'd need to bridge by other means, and that might be mechanical or what we call a safety instrumented function, which is a completely independent system that has levels of safety integrity levels, which undergoes strict requirements as well for testing. But applying LOPA principles would really help to ensure that all IPLs that are there to protect your facility are maintained and they're healthy to ensure that the plant is protected. So fully recommend every industry or any facility undergoing a LOPA and undergoing this sort of technique to ensure that they are looking after their IPLs as they should be.
One more quick question pop in here, and what is the frequency of a LOPA that you recommend? You referenced to perform in association with the HAZOP. Is that saying about every 5 years or every process change, or what do you think in terms of when to perform these?
Yeah, I'd say every 5 years. So you typically perform it as a validation exercise. So those facilities that are undergoing their renewal every 5 years, you would integrate that LOPA with your HAZOP, for example. It's a really good way of just making sure that you've got adequate protection. Likewise, if you have any design changes, so your management change should ideally capture this, or any changes you implement on site, or any additional equipment, they must undergo a HAZOP, not only to identify the hazards and operability problems potentially with your system, but to look at the upstream and downstream effects of installing this system. So that's when I'd also recommend doing a HAZOP and LOPA study too.
Great. Okay, that's all the questions we have, Greg. Thank you everybody for joining us today, and thanks to Greg for sharing his knowledge and wisdom at this topic. The recording of this webinar will be emailed to attendees as well as posted to Protect's website and YouTube channel for you to share with your colleagues. If you're interested in having us conduct HAZOP, LOPA, or provide support of any functional safety services at your company, please reach out to Greg, myself, or a Protect representative. Thank you.